Experiments in Physics with Dr. Frank Oppenheimer. A brief demonstration of the equipment used in the Library of Experiments in Physics, produced in cooperation with University of Colorado Television. Today's experiment
in this experiment of field mapping, one finds the lines of force that would exist around charged electrodes, or, for that matter, around certain shaped pole pieces of a magnetic field. One runs a current through a stainless steel sheet such as this. This part corresponds to the gap in the field, and the cutout part corresponds to the shape of the electrodes. As the current flows from here to here, the potential will vary as the sheet gets narrower, and therefore the shape of the equipotentials will correspond to the lines of force which would leave such an electrode and go over to a symmetric electrode. In other words, this line here is a line of equipotential in the electrostatic field case and would correspond to another electrode exactly the same shape opposite this, or an infinite plane along this line. So that this sheet would then correspond to the field, give you the field between two hemispherical electrodes. The sheet is clamped into a device such as this, of which there probably will be several models. It's clamped down at the ends here. The current comes in at one of these electrodes. This is the positive one here. It comes in through this, flows around, and is through this constriction, and then spreads out again here, so the potential will vary more rapidly along here than it does in this region. These can be placed any place along this edge. If this is the interesting region here, it's probably worth just placing these as far away as possible over in the opposite corner here. And when you do that, give them a little turn to be sure that they make good contact. Then there's another pair of electrodes, this one here, which goes to a galvanometer, and a probe, one end of which can be just used as a plain probe, and the other just has a ballpoint pin in it. They both go to the galvanometer, which is here, and that you have to turn on the light. The galvanometer has a switch on it, which can be set in a variety of positions. Normally it's kept shorted, which protects the galvanometer. If one wants to start using it, one has to put it at any given sensitivity. As you change the sensitivity, look at the galvanometer and make sure that there are no major deflections. Then one wants to set the zero. One can set it actually at zero, or since in this experiment one will want several points all in the same, it's good to set it as far to one side as possible. It won't go quite much further than that, so I'll set it with this knob on top here, the zero set. I'll set it exactly on 3. And now before I do anything else, I'll short it. The power for this device comes from this supply here. It's a regulated DC supply. Before turning it on, I'll turn the main control down and switch it on. Then I will raise the current. The current is coming up here, up to use a standard, say 1 amp. It's relatively immaterial what the standard is, but one wants to constant throughout the experiment. This is a protective device. It's a maximum current limitation. If I turn it down, it'll start to decrease the current, and that right there is the maximum set on the current. If I turn it any more, it'll turn it off automatically. So having found that place, which limits it to 1 amp, I'll increase it just a little bit, and then turn this down and start over again and set it at 1 amp and leave it there. In addition to the power supply, there's a fixed resistor, because this is a high voltage and the sheet has an almost negligible resistance, which always has to be in the circuit. One doesn't use the slide. It comes in here, comes out here, and you want to make sure that's in the circuit before you turn on the power supply. Also, always have this so that the coils don't touch the case at any point, or there'll be a short which could burn out one of the coils or hurt the power supply. Having got the current set at 1 amp, we can then start the experiment. And I think to do that, let's look down on the top of this. The current is coming in from over here. It's passing along through here. And the interesting field region will probably be a region of this around in here. And so we will mark off positions of equal potential drop along here, and then draw from each one lines of constant potential which go to here. These lines of constant potential then correspond to the field lines of the electrostatic case from such an electrode. To do that, we'll set this at some convenient place. Doesn't matter exactly where. And, well, let's see what sensitivity. Let's put it on here and use this end as a probe. You want to be sure this is relatively clean so that there's no contact resistance, and move this along over the region that's interested. Well, I only got a very small deflection there, and that won't enable me to divide it, so I will go to one more sensitivity, 100th of the maximum sensitivity. And now move along here, and now I have a reasonable sensitivity. Suppose I make a mark every division on that, so that as the potential, here's the 0 of my potential, I'll make 1 unit here at 2, make a little mark. I want to stay as close to the edge as possible. Make another one over here, make a mark, make another one at 0, and make a little mark, and keep that up clear across here till I've used up all the space that I'm interested in. I won't do any more of that now. Now I have a series of steps of equal potential drop, and I can draw the lines from each one, starting from this point here and going on. Let me move that. I'll raise this wooden bar and slide this over to one of these other ones. Let me start here, put the point right on my little mark, and then find lines of constant potential. Suppose I move over here. If I move off, how far do I have to move off till I see a deflection? Well, I get only a small deflection by moving a ½ an inch, so I think I need a little more sensitivity. Now I've moved off there. I get one unit deflection with about 1/8 of an inch, so I should be able then to draw a line of constant potential by trying to keep this ballpoint pen exactly at the line of 0, that is with this point right here on 3. As I do that, I'll watch the galvanometer and I'll move away, and if that moves more than 1 millimeter or so away from 3, I'll correct it. And now I'm drawing a line, and it's a little wiggly, but even those little wiggles are less than about a 32nd of an inch. And I can keep that right about on 3. As I move along here, keep correcting it if I get off a little bit. And now my ballpoint pen is following a line of constant potential and making a mark. And then I'll come across here. I could, of course, have greater sensitivity, but it wouldn't make a much better line, much smoother line, because it would be hard to keep right on the 0 anyway. Now I've gone clear over to the electrode, and I have a line that goes along here. I don't know if you can see it. Perhaps I should, at least for the TV experiment, mark that more plainly. It started here, and I'm just following the ink line that the ballpoint pen made, and came along over like that, and came over into the electrode there. And now you can see here is one of the lines of constant potential in this current situation, which corresponds to a line of force in the electrostatic situation. And if I get a whole series of these from the ones I've marked off, where the field is strong, these will be crowded together. Where the electric field is weak, these will be lines of constant elect potential here or field lines will be far apart. One can do this for a variety of different electrodes. It's possible to cut out this edge as well as that edge and imagine a floating object in between two other electrodes. Be sure always that before you leave the apparatus, before you make any changes, that the galvanometer is shorted, and that this is always left into the hole here, because if I now, at this great sensitivity, laid that down on the plate here, it would send the galvanometer off scale and might injure the suspension. That's all there is to this experiment.
Experiments in Physics with Dr. Frank Oppenheimer was produced in cooperation with University of Colorado Television. This is University of Colorado Television.